It's a super cool project where we actually get to start doing some compiling. So what this project does is compiles LLVMlite to X86lite into and it the final output is actually then able to be input to the simulator that we've previously implemented elsewhere, not in this repository. But ultimately, we're looking to spit out a program, and the program is broken up into both the data segment and the text segment. um, yup. And then the data segment we didn't really need to handle. It was on the more simple side, but here we're compiling a function. Um, we kind of naively chose to not worry about optimizations and stuff. So everything gets all arguments in all kind of intermediate values. So all results, like whenever we do an add instruction, that output gets a space on the stack. So we always have access to all of the pieces that we may need. So here the prologue just sets up the stack frame. Then we move all of our arguments to the proper places. Um, so yep. And then here we actually do the compiling of our blocks. So I guess I'll take a step back and explain that a little bit. In particularly in assembly, where it doesn't read quite as nicely as a higher level language, you can see the program get broken up into these block. Well, every function is the function name is essentially a sort of a label which points to some little block of instructions, and then depending on the function that you're handling, that may then point to other blocks of itty bitty instructions, blocks of instructions, which then, when properly put together, are able to implement more complicated functions. So I guess you can imagine a for loop might be broken up into a variety of different blocks, where one block might be checking the condition, and then another block might be doing the body, and then you'd have a block prior to the condition, so everything that happens before your for loop, and then you'd also have a block for everything that comes afterwards. Uh, so hopefully that makes sense. Um, yeah, that's control flow graphs. Um, and each of those blocks are then broken up into, other than the, well, kind of. Each of those blocks are then broken up into three pieces: a label, some way to reference it, which may be in like a function local label, or it might be a global label like the actual function name. Then you got just the block of collection of instructions, and then lastly, they always end with a terminator, whether that's return or branch or CBR, like BR or CBR. Um, but yeah, so here this is where our naive implementation, using just the stack kind of blindly. Um, this is where we set up, given some arguments and all the instructions that we're going to need to handle, which are in our control flow graph. It's going to assign stack slots for each of them, each of those like intermediate values and the actual arguments themselves, which is super useful for at least this implementation. Uh, then here, this is where we compile the terminators. Again, we handle return, branch, and CBR. And again, this is a compiler from LLVMlite to X86lite. So all we're doing is changing LLVM instructions to X86 instructions, which is why you have these collection of guys here. I guess one of the cooler parts of this was compile instruction, where we kind of grouped all of the binary operations into a single kind of class, where we had this function to kind of translate things, because they're all pretty much copy paste the same. And then we have allocate, which is dynamic stack allocation, which is not handled by our our stack layout, which was done beforehand, shown beforehand. Then loading something from the stack, storing to something from the stack, comparing values, call typecasting, and get element pointer, which was a bit of a headache to implement, but in effect, what get element pointer does is allows you, it gets the pointer that's deeply nested within some kind of more complicated object. So you can think of an array, and each element in the array might be structs, and each struct might have arrays and value like integers, and maybe more structs and more arrays or whatever. And maybe you want to go all the way in to some specific value. So maybe something like a more simple example is maybe you have some object that like represents a person, and maybe the person has hobbies, and within each hobby maybe there's a collection of skills, and maybe you want to get access to maybe their I don't know, woodworking abilities or something. So you have to go through the data structure, and ultimately this returns the pointer that you described in the path, which is parameters. So here, this is the actual implementation. We do a little bit of type checking, and then we, we do exactly what it asks. In effect, there's only really two cases: the struct and the array case, and those are each handled separately, but pretty nice. That doesn't need to be noted. I guess here, compile call. We do type verification, and then we compile our arguments. I guess something to note here is some functions return values and some functions don't. So void versus non-void. So depending on that, we may need to add an extra instruction to actually move the value that's returned to a place on the stack, because everything gets its place on the stack, so long as it has a return. And then additionally, we have to worry about stack alignment, which is handled here, and that's kind of extended when you put arguments on the stack, meaning over 6 arguments. The calling convention is that the first 6 get a place in some specific collection of registers, and then the rest of them go on the stack, and depending on the number that go on the stack, we might have to then still worry about alignment. So we have to handle that. So we add that conditionally and then remove that if that condition was hit. Compiling an operand. Null is just what you'd expect, a null value for the pointer, constant value, which is just an integer, a global ID, which is a place in our data segment, and then a local ID, which is the kind of stack slots, the stack spaces that I've been referring to in our stack layout. And pretty cool assignment, quite a headache to kind of conceptually wrap your head around, but fortunately, as you can see here, I guess I should have run this earlier on, it seems that we implemented this correctly. So I guess take a deep breath and take a look at this if you're at all interested. We'll just let this run out, and we'll call it a day. Boom. There we are. All right. That's it.